I think we're right on time, actually. It is 1 o'clock. Just a couple of small things. We have T-shirts. If you want to buy a T-shirt, you're going to have to pay online to get your T-shirt, because we don't want to have any cash handling here. So check out the website. There's a link on there to a PayPal button to pay, I think it's 20 euros. 20 euros for a T-shirt if you want them. They're in the small room, so you can go and look at them and check the quality of the merchandise before you buy. Right, let's get on with the next speech. There we go. I think it's open now. Okay, so I won't do any introductions this year because I was really crap at it last year, so I'll just say, well, this is Travis Goodspeed, and he's going to talk about hardware hacking, and enjoy.
Howdy, y'all. Can everyone hear me? Yep. Okay, so we'll be talking about these things today. This particular model came from a friend of mine in Slovenia. It's a complete computer with a radio that can run for a year on some AA batteries and is networked by IPv6. The manufacturing cost for this is rather low, so you can buy them in small quantities for as little as 40 euro. And if you were to manufacture your own in large quantities, you might be able to get it as low as 5 euro. In each of these devices, you've got a chip which acts as a low-power radio, and you might also have a separate microcontroller. Or in the case of this particular model, they've been combined into a single chip, the Chipcon 2430. The question comes up, though, when you have 1,000 of these scattered out in a field doing something, and that something might be managing landmines, or it might be managing electric meters, or maybe you just want to know what the temperature is at every spot in a room. When you have them deployed like that, they're open to an attacker both over the network and physically. So in addition to anything funky that I might be able to do over the radio or be able to do through IPv6, I'm also able to steal one of these units. And it's very difficult to automate detecting whether a unit has been stolen or whether it just died of battery loss or old age or things like that, because these are built with cheap components. They're meant to be disposable. So I will spend the first half of this lecture explaining how to steal keys from this chip, using an attack that I came up with and first presented at Black Hat Vegas. And I'll also be talking a little bit about this device, which is the GoodFET 20. These are two boards that have yet to be broken apart. This is a JTAG adapter that also allows for the debugging of chips of weird protocols. So if you want to debug the Chipcon 2430, you have to buy either an adapter from my friend in Slovenia, or you have to buy an adapter from Texas Instruments, the manufacturer. Or you can build this open source project, pay no markup whatsoever, and you can debug it. You can start talking to it, you can set bytes in memory, you can clear bytes, you can erase it, and then you can find mistakes in the debugging protocol. And it should be obvious to anyone who's looked at this sort of technology that when a JTAG port is open, the firmware can be dumped out. Many of you have done this to repair a broken router. So if you have a home router and you throw Linux on it and you fail the firmware upgrade, you can use a JTAG adapter, which you might build for a PC parallel port, to reflash it. And on many chips, there are defense mechanisms against this. So you can lock out a board, or a chip rather, and prevent it from being accessed again. In the case of this board, it uses the MSP430 F1612. If you wanted to tap by JTAG, the pins are just up here, and there's a fuse inside that you can blow to keep an attacker out. Well, on the reverse side of this board, there's a chip which allows me to mess with the voltage of the chip I'm trying to debug. And this lets me skip the fuse jack. You can also skip instructions in a bootloader. So while many of you are quite familiar with how to write software that's secure globally, you're assuming that every instruction will be executed correctly. How certain are you that you could write a program that's secure if an attacker has, say, 1% chance of skipping any given instruction? So continuing with this lecture, we'll be talking about wireless sensor networks. A wireless sensor network is a collection of the device I showed you on the first slide. It's composed of chips like these. There's the Chipcon 2430, which is this one on the bottom. It's an 8051 microcontroller combined with a radio. So you write firmware in Intel 8051 machine language, you load it on here, and it has registers for sending packets, registers for choosing the frequency of broadcast or reception, registers for power management, so you can make it shut down and go to sleep for a while. And there's also a register which holds an AES-128 key for hardware accelerated cryptography. And this is necessary because the 8051 is a slow microcontroller. It doesn't have the power to implement cryptography, even symmetric cryptography in software. So instead, that's delegated to hardware. This also means that it's very difficult to use anything but AES-128 on this chip. And it means that it's very difficult to use anything but this implementation of AES-128 on the chip. The Chipcon 2431 is actually the same chip, but with preloaded software. So if you want to build one of these devices, but you don't want to spend the time to write your own firmware, you buy a chip which has all of that preloaded. You solder that onto your board, and then you connect to it over the network. This would be akin to buying a motherboard with Linux pre-installed, not actually knowing what's running on it. So the firmware to this hasn't been audited outside of the manufacturer. If there are problems with it, we don't yet know. And then the Ember EM250 is up here on the top left. It's relevant because it was assumed that this chip had fixed all of the problems with the previous generation, but this assumption had no basis. I had published an attack on the Chipcon 2420, and I got all of these nasty comments and replies saying, no, the electric grid is secure because the electric meters use the EM250 instead. But as you'll see later, it's actually the least secure of these chips. It is worse than the first generation series. A very friendly company, though. When I notified them of this problem, they replied within an hour, and they didn't try to downplay it or spin it in any way. So there was the first generation chips in this family. You had the Chipcon 2420 and the Ember 2420. And at this point, the two companies collaborated on building the same chip. So whether the prefix is CC or EM, it's the same die inside the packaging. The Ember 2420 is no longer manufactured, so it's much more difficult and expensive to find that part, while the Chipcon 2420 is still manufactured in bulk. In the second generation chips, they added the microcontroller to the radio internally. So the first generation, you had two separate chips on the board. You would have, say, a Chipcon 2420, and you would have a PIC or an AVR or an MSP430 microcontroller. The code would run inside of the microcontroller, and the radio would only be used as a peripheral device. So in the first half of this, I'll show you how to break every one of those, which amounts to every Zigbee chip of consequence that is available on the market today. I haven't yet broken the upcoming third generation, but they will be, as soon as I get some samples to play with. And then in the second half of this lecture, I'll talk about wireless sensors in general, and things that you can do on the board level rather than the chip level. And a lot of this comes from the fact that in embedded systems, no one has to worry about security in the same way that they do in IT. So in IT, we have people whose job it is to sit and make sure that the server is always running. And if the server is broken into, well, it's your server, it's in your server room, your customers are connecting to it, it's a big hassle to your business. In chip manufacturing, it's very different, because if a company sells you a chip and you release a product with it, and there's a problem with that product, it never goes back to them directly. In the case of firmware security, a chip being able to keep an attacker from reading its software out, if it's broken, it's very rare that anyone will know how or where it was broken. It's not as if they're connecting to you, it's not as if you have logs that you can keep, or that the manufacturer knows everything that happens with the product after it ships. So the sorts of problems that are found are trivial, and they can't be repaired after the fact. In the case of the problems that I'll present in the first half, there are hardware issues with these chips. In order to repair them, you have to release new hardware revisions of the chip. You have to ship those new chips to a customer, and the customer has to refabricate every board that contains the chip. In practice, this means that it will not be patched. A recall cannot be afforded. The margins are too slim, it's impossible. So this problem will remain, and unless these problems are caught early, they're never fixed. I was at a meeting once, and a guy was sitting at the board going through his CISP training. And all he kept writing was the CIA acronym that they study. And I got bored and I started doodling, as I sometimes do in meetings. But I realized that on these sorts of chips, when they are trying to build the security models, the only thing that they're trying to keep confidential is the software inside of the chip. So if I give you a chip, as the manufacturer, I am only responsible for making sure that your competitor cannot clone your board, or at least that he can't do it too easily. In order to do that, I protect flash memory. I don't protect RAM, because there's nothing in RAM that your competitor could use to help clone your product. That's the source of a lot of this stuff. And as far as the protections for these things, this is from an electric power meter that uses Zigbee technology in the state of Florida. Breaking into this meter is a $150 fine plus the cost of repair, replacement, and investigation. So if you just confess the crime at City Hall immediately, pay for the replacement, it's done, and this is the only sort of tamper resistance that can be afforded. Only recently are they beginning to come out with tamper protecting level sensors. So if you tilt the meter, it recognizes that it's being broken into. But when they implement features like that, there's always the question of what their action should be. And the meter cannot self-destruct because that would make them too unreliable when the servicemen come out and tilt them. So instead, they just flash an alarm somewhere across the city. Now, the smart meters themselves, or any sort of wireless sensor network, will be connected to multiple networks. Meters are a bit different because they connect to the home area network, in addition to their own network of meters. So if you have a smart electric meter on the side of your house, it will communicate with your thermostat, your washer, your dryer, your refrigerator, and the other things that consume power within your home, and it will forward the price of electricity to you. Then they also communicate with each other in order to forward billing data back to the electric utility and to get pricing information from the electric utility. Which means that they have two very complicated types of networking implemented on a single device. The odds of them getting that right on both ends are nil. They won't get it right. And they're also limited in their protocols by the protocols supported by the chips. They can't use any type of cryptography other than AES-128 because chips are only shipping with AES-128 support. This isn't an issue because AES-128 is broken in some way mathematically. It's an issue because their implementations suck, and they can't afford to do anything asymmetric. So if I rip my thermostat off of my wall, and it has the rights to speak to my electric meter over the home network, I now have the rights to impersonate the thermostat. I can then talk directly to my meter, and I can do it without ever touching the meter or tripping its self-defense mechanisms. As far as the Ember 250, which is the most popular radio within an electric smart meter, at least in the United States, I'm not sure about Europe, there is no protection, and I'll get to that in a minute. In the case of the ChipCon 2430, 2530, and every other chip they have ever shipped that contains a microcontroller core, the keys are easily extracted because the compiler moves all data from flash memory into RAM at startup. It's an 8051 chip, which is Harvard architecture. So you have two memories instead of one. You have instruction memory and you have data memory. Instruction memory cannot be read easily as data. There's a 2 clock cycle penalty for reading it. But more importantly, the C programming language demands that all pointers be compatible with one another. And if you have 2 memories, and you have 2 instructions for fetching the value at a pointer, the compiler has to know which instruction to use. The way it does this is it just copies everything into data memory, and then it fetches it from there as needed. And all of data memory on this chip is in RAM. All of data memory is unprotected. So to steal the keys from it, all you have to do is turn it on, allow it to associate to the network, then connect with the debugger, order it to erase all of its memory, which is the only thing that you're allowed to do before, once you've been locked out, that's the only command you're allowed to run. And then once it's erased all of memory, which meaning that every single bit of flash memory is a 1, data memory is uncorrupted and you can read anything you like out of it. And this is true on everything they've ever shipped. I'll talk a lot about different chips. Every vendor is planning to have a new chip coming out soon that's better. And I do a lot of examples with the MSP430 because I'm familiar with it. And I like the chip. I'm not saying that any one of these chips is worse than its competitors, except as I'm directly comparing Ember and ChipCon. And they're both so broken that it's irrelevant. Don't assume that another competitor to these chips is secure just because I'm demonstrating that these chips are not. So to briefly, very briefly review, this part's boring, so I'm not going to waste your time with it. The microcontroller is a computer. It'll be an 8 or 16-bit computer with no user-land kernel separation at all. So you just have a single application running. You have no function tables or a heap or any of the things you would expect in a PC because you don't have room for them. You don't have dynamic linking because you can't afford it. Therefore, you have no reason to have function tables. Everything is statically linked. Every routine that would normally be held within an operating system kernel is instead just a function, and often even an inline function. So whereas normally you would expect a call to an I/O port to, say, trip something, to trip an interrupt handler in the kernel, and for that to figure out what to copy where. On this chip, all you do is write a value to the target of a pointer. If you want to write it to, say, the port 1 output, you just write a byte into memory at 0x0075. And that address, 0075, is the address of the physical pins on the chip. If you were to put all 1s on them, all the lines would go high. All 0s, they all drop low. So you have very immediate access to the machine, but you don't have the separation layers that you would expect on a PC. And things like address layout randomization are useless because you have so little memory that an attacker knows which part of that will be valid. And the wireless sensors themselves are just a radio plugged into a microcontroller, perhaps with some sensing equipment on the side. This is one from the Swiss Alps. There's a sensor connector here, which runs into a temperature sensor that's drilled into the ice. And then you have a computer and a radio here. This board itself is a standalone wireless sensor that connects to the rest of it only for the sensing interface, the battery, and a secure digital card adapter for logging. And there are a couple of different terms that I might use. Zigbee refers to the upper layers, but I use the term a bit imprecisely. So when I say Zigbee, I mean both the higher layer levels of the Zigbee standard, which is a competitor to IPv6 in this domain, and also the lower layers, like 802.15.4, which is the standard that applies to the radio chip itself and to the MAC protocol rather than to the higher layer levels that can be swapped out by software. And when I say a first generation radio, I mean a radio chip that is just a radio, as opposed to a second generation one, which is a radio chip that also contains a microcontroller. Um, okay, so there were the two chips, they're the same, and they were just a radio. You would send a key over a serial port, SPI, which is a synchronous serial port. But it's sent as clear text and you can packet snip it. You can stick two syringes into the board and you can watch the microcontrollers send the AS128 key to the radio. And at this point they were all being advertised. We have security, we have AS128, 128 hasn't been broken yet. You don't have to worry about anything. But the fact was that if you stuck two syringes into a single unit and stuck them in a way that actually can't be detected electrically with the chips used, at least with only a software patch, you could get all of the keys that you would need. And the networking protocols at this time would all share the same key. So not only are you allowed to impersonate the device that you stuck the needles into, but you can also impersonate anything else in the network. And all you have to do is stick needles into the test points in the board, or if the test points are unavailable, I use 20-gauge hypodermic syringes, which are sharp enough to dig into that little column of solder on the chip itself and hang on when there is no test point. So the defender doesn't really have the option of not applying test points. Sometimes they'll try epoxy, but when you do this, you see on your oscilloscope the actual traffic going across. So here we have 2 bytes being sent, and this is on the clock line. The data is written by each party on the rising edge, and then they sample it on the falling edge. This is traffic coming across. I believe this is 1 byte that's been zoomed in, but I'd have to measure it to see. So you just overlay the two on one another, and then you can watch all of the traffic. Or you can purchase a device commercially from a company called Total Phase. This is a screenshot from the client to their Beagle. The Beagle can sniff as quickly as these chips can speak to one another, so you don't have to worry about losing packets that way. And you can see this hexadecimal traffic is everything that's been sent between them. It's a bit too fine for you to see from back there, but I'm only seeing one part of the conversation because I've only stuck 2 syringes in. So I see everything that the host sends to the radio, but I don't see any of the replies. All that would take is an extra syringe. You stick 3 in the board and you see the entire conversation. But you don't need the 3rd because you only need the key. With the key, you can begin to participate in the network. This article I published is a quick little blog post. Like, hey, here's the thing, you stick your needles in here, that's why this particular chip is insecure. I didn't mention applications or the smart grid or anything like that, but this was at the same time that CNN ran a story on the smart grid. And the two got confused in the lay press, because when you're writing an article for a newspaper, you can't include technical details. So every time anything in science, and particularly in security, is reported, there's this tendency to say, oh God, the aliens are coming, and it's because of this one little thing, when the actual argument is very different and more complicated than that. And so on this post that didn't specify anything about the smart grid, I got a post by this guy named Bruce. I don't know his last name, but I've heard since putting this in my slides that he's some higher up at the Zigbee committee. But he says, the vast majority of pilots and products out there that support the Zigbee Smart Energy Profile, which is what are used in electric meters, are based on the Ember 250 and not the TI Chipcon 2420. Utilities are requiring the security and standardization that the Smart Energy Profile provides. And he also says down here at the end, I consider this blog to be cute, however it is shown that politicians with mediocre minds will overreact to anything that serves their purpose. So because he's calling me cute and that's kind of creepy, I had to break this chip too. So I looked up the datasheet, and it uses the XAP2 microcontroller, which is a very obscure unit that hasn't been deployed recently or in many other products. It has 128 kilobytes of flash and 5 kilobytes of RAM. It has hardware accelerated AES, as all of these chips do. And it has low power when sleeping, as everything else does. But So his argument was that because not a clear or well-reasoned argument, mind you. His argument was that the ChipCon 2420 was vulnerable. He conceded that. But he said that the Ember 250 was not vulnerable because it didn't expose its keys by SPI. There was no wire that you could stick needles into to watch the keys being loaded. So because of this, he concluded that the Ember 250 was secure because the committee had decreed it to be secure. The reason why this is wrong is because there's a JTAG port, and this JTAG port was made by a small consulting firm that was making its second chip. And I believe this was their first chip design that was ever released commercially. It is also important because the XAP2 is designed to be thrown into any other chip. So if you're manufacturing a sound card or something, and you need to add an extra microcontroller into that same chip, you can get their design as Verilog code, compile it into your chip, and then ship it. So their design knows nothing about the underlying process that you're using to manufacture your chip. They don't know which chemicals are going into the die. All they're specifying is high-level source code for it. So in this high-level source code, you build what's called a register transfer language description, which just describes how different things plug into each other and what sorts of gates are between them. There is no way to describe a fuse in a register transfer language. And there's no way to describe a single bit of EEPROM. So making anything permanent requires that you talk to outside memory. And talking to outside memory, you have to do over a memory bus. Accessing a memory bus is complicated. Not too complicated for a microcontroller, but it takes a lot of code to grab a value from memory and load a register with it. So when the chip is being programmed by its serial port or by radio, it might have some defense mechanisms, but when you program it by JTAG, or the Insight port as they call it, which is this plug here, and it's standardized. You'll have these exact 10 pins on every board that uses this chip. In order to break into it, all you have to do is buy the debugging box, plug it up to the board, and ask for a copy of all of memory. Because they never implemented a fuse or a protection bit or anything else to defend the chip. As a manufacturer of a board, there's absolutely no way that you can tell the chip not to accept further debugging connections. None at all. So this is actually more vulnerable than the chip I was picking on earlier, because not only can you get keys out, you can also get all of the programming out, patch it, return it, and you don't have to do anything tricky to do it. You just plug it up and request it out. But at the time I discovered this, I was hoping to have some sort of a challenge, and instead all I had to do was read the data sheet and then it was done. So because this was so boring to break, and because the company was so friendly when I reported the problem, I thought, shit, I've got to break their competitor's product too. So I grabbed the ChipCon 2430, which is the second generation chip from Texas Instruments. And internally this uses the same microprocessor as every other second generation chip that this firm has shipped. So just like the M250, you have an 802.15.4 radio, but instead of the XAP2 microcontroller, you have an 8051 microcontroller, which is very, very distantly related to x86. It's debugged over an SPI-like protocol, except that the data lines are shared onto a single pin. So this is the target board that I attacked. You plug voltage and ground to it, and then it runs IPv6. You can ping it, you can send UDP packets to it, you can do all of that fun stuff. It's not big enough to run SSH, but that's not the purpose of it. You would use cryptography in another area. when you debug it, there's an initialization sequence that you have to run. So you first connect, and then you twiddle some line voltages to cause it to enter its debugging phase. And this is always allowed. Once you're in, there are different commands that you can run. You can erase the entire chip. You can get a copy of the program counter. You can debug an instruction, which just executes code that you give it instead of what it would be fetching from instruction memory. You can also request its version ID. And then it sends you a reply. And in your command, you specify how much of a reply you like. So I took the GoodFet, the board that I mentioned at the beginning, and I implemented software for debugging this chip. So that instead of having to use anyone else's debugger, I could use my own. And as part of this, in writing all of the code for it, I knew where everything was in the software. So to initialize it, I do this. All I do is I pull the inverted reset line low, which sort of pauses the chip and makes it get ready to start executing from a fresh start. This is how you reboot the chip. But while this is low, I send 2 pulses on the debugging clock line. Then when I bring it high, it begins in debugging mode. Then I send traffic to it. It's big endian. Yeah, it's big endian and its most significant bit first, which is very handy because everything is sent just as you would write it on paper. So on every rising edge, a bit is written to the port, and on every falling edge, it's sampled. So if you were writing it and you wanted to write 34, you'd wait until this edge to assert the line. There's a little delay in between, and then when the clock line falls, the data line is sampled. So the 1 is written here, and it's sampled here. And you continue for the rest of the bits. And the master, which is the debugging device, in my case, the GoodFet board, always speaks first. And then there's a reply to it from the slave device. The instruction itself is just a single byte, 1 bit of which specifies whether or not you want to reply, 2 bits of which describe whether or not you're sending extra bytes of parameters. Like if you want to execute an instruction with the debug instruction command, you would send executable code in those object bytes. And then it will return an optional byte, or it won't, but it never returns more than 1. And then there's a lock bit, and this is what Ember forgot to put in. The way the lock bit works is that a particular address of flash memory is loaded into a register as the chip turns on. And then that register is looked at whenever you attempt to debug the chip. When it's locked, you're allowed to run only these 3 commands. You can request the name of the chip. You can erase the chip, or you can request the status of the chip. But you're not allowed to run foreign code. You're not allowed to read and write memory. You're not allowed to skip an instruction. You're not allowed to read the program counter. You're not allowed to do any of the things that might make it easy for you to break the chip. You're only allowed to erase it, and then their thinking was that after the chip has been erased, there's nothing left for you to take. So there's no harm in allowing you to erase the chip. It's also necessary to allow erasure because if you do allow erasure and a device is broken in the field, a field technician can perform an update without having the rights to rip anything out of the device. The problem is that the chip erasure command only erases flash memory. And this is by design. They specify this in the manual. This was not an implementation mistake. So while it erases all of firmware, including the security bit, it doesn't erase RAM. And on the Intel 8051, the core that they chose to use, all of data memory is in RAM. And all of executable memory, all of instruction memory is in flash or in permanent ROM. So you have this division, and you have 2 types of pointers. A function pointer always points to instruction memory, and a data pointer always points to data memory. If you try to resolve a function pointer to a byte, in C, instead of getting the first byte of that function, you will get the byte that's in RAM at the same address as the function is. But that has nothing to do with the function. There are two separate memories that just happen to have overlapping addresses. And pointers have to be compatible with one another in C. You have to be able to pass a string to printf without it doing a condition or calling another function to figure out which memory that string is located in. So in Harvard memory, you have this division, as opposed to von Neumann chips, where everything is combined into a single memory. Like on a PC, if you have a pointer to a function and you resolve it, you can read that function. There's also the issue of whether RAM is executable. So in Harvard, you're not able to execute RAM. And this is all forced by the compiler. Every compiler by every vendor. This is not specific to the compilers of this chip. Every compiler for every Harvard chip will move every constant, even those that are never written to, into RAM, including keys. So in order to exploit this chip, all you have to do is erase the chip, then tell it to dump all of the data, and pipe that into a file. Then you have a copy of 8 kilobytes of RAM. The key is probably in the last 4 kilobytes of RAM because of power management issues. The upper 4 are known to be good between low power modes. So if you sleep for a little while, that part is safe, while the lower 4 will be wiped out. So when I reported this to TI ChipCon, they came back to me and they said, well, 4 kilobytes is a lot of memory, and there are 8 kilobytes of RAM total. How could anyone possibly find a key in all of that? And I thought about it for a second, and I thought, well, you can use, you can look for the entropy. So those 4 kilobytes will be, sorry, the 128 bits of the key will be perfectly random, while the rest of RAM won't. But then I thought, how long would it take to brute force it in Python? So I called up Josh Wright, and I said, hey, I've got this exploit. Here's how it works. Tell me how long it would be in Python. Because he's doing a Zigbee tool called Killer Bee that will be released at a later conference. And he called me back, and he said, 4 seconds. And this is just doing a sliding window. You take a window 128 bits wide, and you just slide that by 8 bits at a time, assuming that the key will be byte aligned. And you compare that against some packets that you've sniffed but have not yet decrypted until those packets make sense. And in 2 seconds, it can check the part of RAM that the compiler will move things to by default. In 4 seconds, it can check all of RAM. Now, there's actually a way to defend against this in software, and that's why I was so ticked off at ChipCon for not informing their customers of this, because if you have a black eye and there's no way to fix it, I can understand wanting to keep quiet, but in this case, you can change your memory allocation by preprocessor directives in C. So if you had a constant string foo, which was hello world, and you put this little word here in it, underscore underscore code, then it stores it in code memory instead of in RAM. This means that it's in flash memory, so you're not able to freely read and write it. But at the same time, it is protected in that the attacker cannot read it without bypassing the security bit. It's not enough to just erase all of memory, because that would erase this string too. And they even did an application note, DN200. Their very first application note was on how to do this to save RAM. They didn't intend to do it for security reasons. They had the issue that with 8 kilobytes of RAM, sometimes they would run out of RAM. And they would have a stack overflow, not in the sense of a stack pointer overflow, but in the sense of the stack actually growing so deep that it collided into the bottom of RAM. which is never good for a machine. So they released this, and so they had their own documentation to point to. They could say, look, if you're trying to do something secure with our chip, you have to look at this application note and you have to make damn sure that everything that you intend to be kept secret is held in here. If you were to store your keys in this part of memory, and you only copied them into the key register, you never copied them into RAM, then when the chip was reset after erasure, it would also erase the key in the register, and the copy of the key in flash memory. It would not leave another in the chip. There are some awkward points about this, though. If you made the string equal hello world and you tried to call printf on it, it won't work. Because the value of foo as an integer is the address in code memory that contains hello world. It's not the address in data memory. And printf will always look in data memory by default. So if you intend to have some strings in flash and other strings in RAM, suppose you want the username to be in RAM, but you want the error messages to be held in flash, you have to have separate printf functions for them. Or if you're doing a full printf with like character substitutions, so you could do the %s to reference a string, well, maybe you'd have to make a capital S refer to a string in code memory. And there are all sorts of other hassles that you have to go through. And it's for that reason that no one actually implements this defense, so far as I know. So to summarize the ChipCon stuff, every chip they've ever shipped prior to the upcoming ChipCon 430 series, which uses the MSP 430 instead of the 8051. Every chip prior to that series is vulnerable. And every application using those chips exposes its keys in this manner. So if you have any Zigbee device that was manufactured prior to a month ago, it's vulnerable to either this attack or the one against the Ember. So the third generations are coming out, and they support more advanced chips. In the case of Ember, they're using the ARM Cortex-M3, which does include a JTAG protection fuse. And this is done as a fuse on the pin, I believe, although I'm not certain at this point. The ChipCon 430 instead uses a tap fuse, and this fuse is implemented in flash memory. So when the ChipCon 430 turns on, it has a little piece of code that copies a control value from flash memory into a register in the JTAG controller. So you become locked out of the JTAG controller just after boot if a particular word in memory is AA55. If it's all zeros or if it's all ones, you're allowed in. This means that if you blow the fuse, you can later unblow it by software. It's very difficult to move a 0 to a 1 bitwise on a machine, but they allow either. So you can inject code that does nothing but blank out those 2 bytes of memory, making them all zeros, and then you can hook up your JTAG debugger. And that would require foreign code execution, but foreign code execution is easy on the MSP 430 because it's allowed to execute RAM. And on the earlier ChipCon 430 chips, there was a vulnerability to the bootloader that I discovered in which you could use a timing attack to figure out how many bytes of your password guess were correct. We'll get to that later. Then there's the issue that this is being loaded by code. So even if we assume that the default state is properly set up such that when you turn the device on, it disallows access until the software enables it, well, what happens if the software has a problem reading flash memory? Well, you can force these problems by messing with the supply voltage. So it might be that the protection fuse works perfectly at 3.3 volts, but doesn't work at 1.5 volts. When flash memory becomes unreadable, but ROM memory, permanent masked ROM, is still readable. And you can drop the voltage very quickly on a single clock edge to make maybe just that fetch from flash memory make a mistake, while all other fetches work fine. This is the Ember 350 block diagram from their documentation. Chips are not yet available in quantity, but they are sampling a few to their development partners at this point. And then this is the ChipCon 430. This is a photo from Texas Instruments, but I think they messed it up, and this is the debugging connector and not the part that they circled. But this chip is both an MSP430 microcontroller and a radio. They have internal samples, and I think they're just now beginning to allow for external samples. I'll be very eager to get one. So to conclude this part, the Zigbee chips that are available are not secure. You can do some things to help defend yourself, but if you're manufacturing a product using this technology, you have to recognize that it's likely an attacker will be able to break in if he ever puts his mind to it. The only things on your side, so far as security goes, involve the lack of script kiddies in this area. So it's not as if everyone has Zigbee equipment in the same way that everyone has Wi-Fi equipment. And in all of these, they equate cryptography to security. In every data sheet, in every marketing manual, they say, we have AES-128 and it has not been broken. Or we're looking at using elliptic curve cryptography and it will save all of this. But in point of fact, they mess up in so many other areas. And they mess up not only at the chip level, as I've shown in this part, but also at the board level, as I'll show you in a minute, that there's not much you can do to defend yourself. So in the second part, I'm just going to jump through a bunch of different vulnerabilities that these have. I might not be able to explain all of this in depth. So if I glance over something that you would like a clearer argument for, or you would like further proof that it works, you can either search my blog for the article that I'm referring to, or you can contact me afterward and I'll send you the full description. But I haven't time remaining in this lecture to explain all of this stuff in depth. The access points themselves are, which connect the low-powered wireless network to another network, such as a cellular network or Ethernet. They usually run embedded Linux, and they don't update it often, if at all. So how many of you would trust a Debian Linux machine that was manufactured 2 years ago? In 5 years, how many of you will trust a Debian Linux machine that was made today? I mean, even OpenBSD on its default install, if you go back far enough, there are remote exploits. 2 of them, but they still exist, and once it comes out, there's nothing that you can do to update all of these because they're out in the field. The original manufacturer doesn't have access, and he doesn't have the resources to allow for automatic updates. And they're usually controlled through a website, so you can do cross-site scripting attacks on the control page for the wireless networks. You can send a link by email, and if they go to the link, it'll go into the administrative page and execute shellcode. The boards themselves have different parts on them that can be exploited. Here we have an MSP430 microcontroller on the left, and we have an SX1211 radio on the right. This is an academic model intended for monitoring permafrost in the Swiss Alps. This chip does not support cryptography. So, and the MSP430 isn't fast enough to support cryptography. So in the field, not only will the radio traffic be unencrypted by necessity with this device, but also there's unencrypted memory here. So if you steal one of these devices, you have a half megabyte of flash that you can tamper with. And there's no way to defend this chip, the flash chip. There is no secure counterpart to this. And all of these custom radios, which were popular 2 years ago, I think, before the AES-128 acceleration stopped costing as much to manufacture. All of them lack cryptography, and they're all slightly non-standard to support vendor lock-in. So if you use the SX1211 or the ChipCon 2500 or another one of these vendor-specific chips, you're stuck with it, and you're not able to upgrade to the standard compliant 802.15.4 without breaking compatibility with all of your old nodes. They can't route between each other, they can't speak to one another. And lacking cryptography doesn't make that much of a difference when the attacker can steal units and extract keys. But not being able to upgrade to cryptography is a very serious issue, because if you deploy a large network with this, you're not able to begin swapping out nodes with more secure ones. And the frequencies that they use will vary by jurisdiction. So in Europe, you'll use 800 megahertz. In the States, we'll use 900. 2.4 gigahertz is popular everywhere, of course. Skip that one. Yeah. You also have expansion connectors on all of these boards and debugging connectors. And once you trace them out, you find a plug that's on every unit that you can easily plug up to and change. In the case of the board from a couple of slides back, it has this connector which connects to a serial port. So you can run this out to your PC and you can actually talk on a shell on the device. And what software they have connected will vary drastically, but it's quite common for them to spit out debugging information as ASCII text at 9600 baud, 8 bits, no parity, and 1 stop bit. Suddenly all of those Hayes modem commands become useful again. You also know which part of the chip contains the lines that you're interested in snooping, and that can't be reconfigured. So in the case of the SX1211, if I'm trying to, say, capture packets, or build a packet sniffer out of a single captured board very quickly, all I have to do is stick a needle into the MISO pin, the MOSI pin, and the SCK pin. These three are on the corner. So I know that I can tap pins 15, 16, and 17 on the upper right corner of the device and get all of the keys out. And I also know that on a given board, the pins will always be the same. So I grab these 3 pins on this corner, and I get all of the traffic. These pins are also easy to identify because they very rarely have support components next to them. You won't have a capacitor or a resistor on this line. Instead, you'll have a few wires parallel to one another coming out of that region of the board and moving toward the microcontroller. As opposed to these other lines, which have capacitors and inductors. And, these parts are very obviously analog signals, while these are very obviously digital. And connecting to them doesn't require soldering. It doesn't require having a lab. All it requires are 2 hypodermic syringes. These are 20 gauge with 2.5-inch barrels. These are rather large syringes. And again, you just stick them in there, and then you can watch everything that goes across. This is a picture of me tapping the, we went over this earlier. So when you do these bus taps, you can catch the crypto, but you can also emulate the radio. You can fuzz test these things. All you have to do is wire in where the radio would be, send fake packets, make sure that the checksums are right so they don't get dropped too soon, and wait for the chip to crash. And you know when it crashes because all of the input-output pins that are selectable, as in they can either be output or they can be input, they all become input pins on a reboot. So if you know that a particular output pin, say a serial port, an unused serial port will always output a 1 on its transmit pin. If you have like a 5 kilo ohm resistor pulling that down to 0, the value will remain a 1 until the chip resets, and then that pin falls down to a 0. And you can watch this. And you can have a fuzzing device watch this. I'm working on a fuzzing toolkit for these devices. So you can just wire into a board, start sending garbage at it by Zigbee, and you wait for it to crash. Once you have a crash, it's actually very easy to extract memory from a chip, even blind. The paper that I presented at the Usenix workshop in offensive technologies, in which I did blind fuzzing to extract the memory from a device by doing return-oriented programming into flash memory, looking for a pop R11 followed by a return, which would elevate my access and put me in the bootloader. And then I could just ask it for a copy of the password. And this works in 3 to 4 seconds. Because memory is so small and the compilers are very regular in what they generate. This is a Landis & Gyr electric meter. And you can see 24C32 is the label on this chip. That means that it's an I2C EEPROM. And ITC is particularly fun because it supports multiple masters. So if you stick a syringe there and a syringe there, and you have shared ground, then you can talk to this chip, you can dump its contents, and you can do this while the board is still running. The master device will actually avoid talking to the chip when it sees that you are already talking to it. It has collision detection and avoidance. This is the parking meter thing that Jake Applebaum presented this morning. I implemented it as well and a little bit earlier, and I did it using just this board running out a serial port. All this board does is watch the I/O pin of the smart card and otherwise connect the two together. So then it spits it out through the serial port. All you have to know to sniff the serial port is what the proper baud rate is. I actually spent more time figuring out the baud rate than anything else on this. In the Philadelphia meters, it's something like 4,355 baud. They changed out a crystal at the last minute in their design. So a crystal was specified that would have been 9,600 baud, but they switched to another. Then there are tools for sniffing the synchronous protocols. This is a bus pirate kit from Hackaday. You can just connect it up to a chip and start talking to it using a terminal emulator. So with Minicom or Hyperterminal, you can talk to the target chip, and you can run any of the commands that it supports. You can talk directly on Zigbee using just a keyboard and a dumb terminal using this device. And because JTAG is implemented in hardware and there are these fuses, there are vulnerabilities to it, but there are also other methods of reading the contents of a chip out. There's often a bootloader, and these bootloaders are sometimes put in masked ROM, which cannot be patched or changed or upgraded. So I started collecting and disassembling these, and then I started annotating the disassembly and looking for the password comparison routine. I wound up building this device, the BSL cracker, which connects to the bootloader, presents a password, and as it presents the password, it makes sure that the receiving device, the victim, is never waiting for a byte to be transmitted. Wherever it would wait for a byte, I make sure that that byte is already being transmitted, and I stretch out the timing a bit to ensure that this doesn't cause any errors. So then the victim device runs in a loop, and it checks all of the different passwords that are available. And if I were to try to brute force it, it would take 128 years, or 32 if you overclock. But with this device, I can figure out how many bytes of my guess are correct by using a timing attack. So I can measure the time of the password comparison, again, making sure that it is waiting, that it never waits for me to send a byte. Then I measure how long the comparisons take. And even if that's disabled, I can use a voltage glitching attack to skip through a bit. In that case, I make it skip a single instruction. So I say, ask it for the password. There's one instruction where it has an if statement. It says, if the privileges aren't sufficient to read this, then skip the read, or send a non-acknowledgement. But if you skip that one instruction, then it sends you the password, and then you know the password, so you never have to run that part again. And you can't have a self-destruct there, because it might accidentally fail. So in the case of the timing attack, I just send a command saying that I want to speak to the device. Then I send then it replies with an acknowledgement. From the rising edge of that acknowledgement, like when it sends the last bit of that acknowledgement, I begin counting. And I keep counting until it tells me that my guess is wrong. And as this is happening, I send out the bytes. And this is done by a program that's in masked ROM from C100 to 1,000 hex. You can just dump it and disassemble it and read it. And then you can reverse engineer it. The password itself is composed of 16-bit pointers to interrupt handlers in memory. They reused the interrupt vector table because they didn't trust the compiler vendors to randomize the password. But then there's the question of how many are actually random. To Thomas Becker and a couple of other German graduate students got together and they figured out there would be 40 bits because of the 256 that are in the password. Suppose that every row is a word of this password. The reset vector, the address at which execution begins, is always the very first byte of flash memory because all the compilers grow code upward from the bottom of flash. And then the least significant bits are always 0 because every instruction is even aligned. If you have a pointer to code, its least significant bit is always a 0. So that much is known. So by this point, we're down to 225 bits. And then most of the interrupt handlers are unused. So in GCC, they will all point to the same address. And in competing compilers, they'll all be ones. Like FFFF, FFFF, FFFF. For every interrupt handler that is never triggered. So if I don't write a handler for a button press or for a clock triggering, both of those will be clear. Both of those will be known in advance. And then because code grows from the bottom of flash memory up, I know that the high bits will most likely be clear because all of the interrupt handlers are in memory beneath that. So all of that will be ones. So only this green area actually needs to be checked. If you run the password comparison in simulation, and I did this by wrapping it, so I just loaded the masked ROM image, and then I told my emulator to pretend that it was RAM, and then I just had C routines that would rewrite bytes of it to make the comparison routine a separate function that I could call, given a challenge. And I tried 256 passwords. I tried 00 repeated, 01 repeated, all the way up to FF repeated. And I counted how many clock cycles they took to execute. Most bytes, in this case, took 6,543. Some others took less. So I took the difference of that, and I divided that difference by 2, because on the graph 2 slides back, the execution path of 2 bytes that were equal was 2 clock cycles faster than one where they were unequal, because it took 2 clock cycles disabling my access. Well, you'll note that if you add these together, you get 32. And 32 is the number of bytes in the password. So this tells me that 00 will appear once, 11 will appear 16 times, and 3A will appear 15 times. I also know that because 11 is odd, it will be the more significant byte, because the less significant byte can never be odd in any given pair. And then I can guess that 1100, being the first word of flash memory, will be the reset vector. So I know of all of these words that most of them are 11.3a, and one of them, one very specific one, is actually 1100, and that's what the password is. Now, in a deployed device, you would use more interrupts, so not all of these would be quite so easy to guess. But that doesn't matter, because in 256 attempts, I've reduced my alphabet to 32 particular bytes, and I know their quantities, so I can just enumerate them. This is a picture of the waveform on a scope, and you would measure from this edge to this edge, the scope showing you what the victim tells the master. There's also the issue of this being a shared password. So if you manufacture 1,000 wireless sensors using the same firmware image, they all have the same password. In Becker's paper where he figured that it would take 32 years to, he figured that it would take 128 years to brute force this. He mentioned a script he had written which would randomize the password. So the way he figured it was that whereas normally an interrupt, let's say the reset vector points to 1100 hex, and then you'd have code at 1100. His script runs through a firmware image, and for every interrupt handler, it picks an unused piece of flash memory. At that place, he puts a branch to the original handler. So that in this case, the password value would be 3A62 instead of 1100. And you can do this on an assembly line. You can patch your production process so that every board you program has a different password. If you search for his name on my blog, you'll find a copy of this script. But the chip is still vulnerable to voltage glitching. this is a CMOS inverter. If A is the input and Q is the output, when A is low, this transistor here will pull Q up to high voltage. And when A is high, this transistor here will open and pull Q down to low voltage. But the decision to open or close is made by a threshold, and that threshold changes with the supply voltage. So if I drop this line, which is attacker controlled, down to half of its present value, then this transistor will mess up. Current will then leak from voltage down to ground, and this falls a lot lower, but only in this region of the circuit. So I can make everything mess up just by making the voltage drop too low just before latches are set. And then the wrong value will be copied from one region of the chip to the next. So in the case of the MSP430 bootloader, there's a little piece of code in it that checks to see whether or not you are allowed to begin the bootloader. So in the more recent versions, if there's a vulnerability in the bootloader, which there is, you can put AA55 into memory at FFBE, and then the bootloader will look to see whether or not that's there. If it is, this JZ plus 0 instruction will jump to itself repeatedly. But what does a jump look like in machine language as it's being executed? How many cycles does it take? Well, on a PC, you never count the cycles of any given instruction because it varies more by cache hits and misses and that sort of stuff. On a microcontroller, all of your code is cached. Everything can be fetched quickly. So the way it works is that a JZ takes 2 clock cycles. It has a rising edge in which it adds 2 to the program counter. So the program counter then points to the upcoming instruction. And then a falling edge at which this program counter plus 2 value is placed back into the program counter. It's at this point that it does the comparison. On the rising edge, it adds 0, that's this parameter to the jump instruction, to the original program counter. And then there's a falling edge at which it overwrites it. Well, what happens if this clock edge messes up? What happens if for that clock edge it thinks that it's actually running an add instruction instead of a jump instruction? Well, the program counter is already pointing to the next instruction. So execution falls out, as if this comparison hadn't been made. And this isn't just any clock edge. This is one clock edge in 4 until the chip resets from old age. So you have many different attempts to hit this. You can do it with a Morse code key and a potentiometer. And then if you are trying to hit it more regularly, there are tricks you can do. This is a scope recording of the voltage line of an MSP430 as I was playing with glitching it. Every time it dips down from this high level, that's another clock edge, because a CMOS chip consumes power on a clock edge. Okay, that's where the heat comes from in your PC chip. If you overclock your PC, it generates more heat, so people do their funky cooling devices. It's the same thing in a microcontroller, except here you're running a lot slower, and it's battery life and not heat output that you're concerned about. But if you watch when this happens, and you multiply that frequency up using a phase-locked loop, you can wind up getting this out in parallel at, say, 16 megahertz, whereas the actual edges come at 2 megahertz. And then you could build a device which would drop the voltage just for the region it needs to be dropped in. You can count clock cycles since the chip begins execution. You can do all of these things to improve the reliability of glitching the chip. And when they're found, you can't patch old shipments. And even with the new shipments, you can't patch them if it means breaking backward compatibility. Ember is unable to fix the Ember 250 chip because they do not control the design of the microcontroller inside of it. The only option is to have a new chip with a new microcontroller. And issues of disclosure come up. They don't do errata sheets for these things. In security, they do it if there's a problem on the analog chain. If you need to add an extra capacitor, they'll tell you about that. But they'll never tell you about an issue with the security of the chip. because that makes them look bad. So all of these chips are blown, and it's really hard to do upgrades to get cryptography right. Tamper detection and resistance are damn near impossible. But what you can do to defend your board is to blow the security fuse. Countless times I've been given a board and they say, hey, can you get the firmware out of it? And I look at the part number and I say, yeah, I think I can. I'll take it home, hook it up to my equipment. Before hooking it up to my BSL cracker, I'll just hook it up to a regular JTAG adapter. And more often than not, I'll see that the fuse hasn't been blown. The security mode is never enabled. And getting the code out of a somewhat secure device is as easy as getting it out of the Ember chip. You can also randomize the BSL passwords, the bootloader passwords, to make sure that individual devices don't share passwords. Yeah, so I've run over a bit, but I'm not keeping anyone out yet. So are there any questions or?
Let's do like the Q&A session. I want to start off by asking you a few questions actually. We've heard about some of the devices that are using these chips today. I mean, basically most electric meters and stuff like that you've been talking about, and
yes.
something measuring permafrost and stuff like that.
Yeah.
But I think we're all curious, what other types of devices have you found these then? Where do you actually find these things today?
Right. So at this point, the technology is rather new. You've been able to buy chips affordably only for a year or two now. So they're not very often deployed in commercial products. You won't find this in cell phones because this technology competes with Bluetooth. And it's a lot easier to add Bluetooth to your cell phone. The reason why I mentioned the permafrost example is that a lot of the targets of this technology are academic. Instead of making a commercial product and needing to make a return on it, they will instead use academic funding knowing that they're going to lose the money. I used, this is used for environmental monitoring a lot. So I had a project where I set up one of these networks to measure the temperature and humidity within a radioactive area. You can't send a person in with a probe, and it's very difficult to run wiring, so it's hard to plug something into a wall outlet. Instead, you can just drop a bunch of these into the contaminated room, and then when their batteries die, then you yank them out and you throw them in a salt pit. So it's a new technology. They're not yet commonly deployed.
All right, but from the looks of it, security implementation is in these things are not moving in the right direction, are they? I mean, are you optimistic about that they actually will solve these things or actually make them better?
No, not at all. There are, I think, 3 of us working on the security of these devices, and every time we look at a chip, it breaks. Like Mike Davis at IOActive did a worm for the smart meters. And when he did it by the traditional techniques of writing a worm, except that he didn't have to worry about user kernel separation, because there is none. He didn't have to worry about stack execution protection, because there is none. All of the defense mechanisms that the IT industry has built up to defend itself from these common attacks don't exist, because they cost money and they cost surface area on the chip to implement. And they cost time to implement. So the defenses are infinitely far behind IT.
Right.
As bad as you think a Windows server is,
right.
This is far worse.
Still, you said that the manufacturer of the, was it EM250 chip, they were pretty nice to you? I mean, they were actually trying to understand what was going wrong anyway.
No, they were great. They'd already identified that problem themselves.
Right.
And when I emailed them about it, they replied within an hour.
You're just embarrassed.
A little bit, but.
All right, and then you talked to the ChipCon guys too.
Took a while.
Did you ever talk to them after? I mean, after you demonstrated that 4-second to find a key and.
Yeah, that was about the time they stopped replying to emails.
You haven't heard any reply to that at all.
No, when I first emailed them, I heard nothing back. So I emailed particularly people at the company, and I said, I know you're listening to me. This is your email address. Howdy, Steve or Bob or whoever it was. Still nothing. So I started emailing all of my friends who were customers of Texas Instruments. And I said, hey, I'm having trouble getting in touch with the Norway office. Could you please hook me up? And then within 2 hours, I got a frantic email from Germany saying they're going to reply to you soon. It's quiet down.
Nice. I mean, of course, I mean, a lot of the security implementation with cryptography would, of course, it would be nice if they had asymmetric cryptography somehow to, solve authentication stuff and like that. But from most of the problems that you've shown, that wouldn't even solve the problem anyway, because they're not protecting the memory. I mean,
right. It would help in cases where it's difficult or dangerous to access the device. So if you use this technology for landmines, asymmetric crypto would help a lot, even if it would help a lot because there's a high cost to extracting the keys from any given device. You have to send the bomb team out, and they might get blown up, and this will be a very important technology for landmines in the coming years because it's illegal by many international treaties to use landmines that might stay around after the war is over, because they last for decades and they continue to kill children after decades. But with a networked set of landmines, you could order them to self-destruct when the conflict is over. When you no longer give a damn about holding that particular area, you can just say, okay, all of you blow up while we have no people here, and then the area is free to be resettled. It can help a lot of people. So. Yeah. Of course, it's terribly inconvenient if it blows up early.
Or if your enemy can tell them to blow up. Yeah. So, I mean, just in general, I mean, since this is hardware security, I mean, what do you think are the biggest misconceptions when it comes to hardware security today?
I think that a lot of software people know of the common software problems. If you do code auditing, you realize that people never check to see whether a size is positive or negative. They keep using unsigned values, so you have integer overflows, and you recognize how vulnerable much software is because you play with it often. And hardware sort of becomes this black box that you don't play with, so you don't know where the vulnerabilities exist. And when you say that's insecure because everything is insecure, and someone says, well, where would it be insecure? Why would it be insecure? Then you find yourself at a loss, even if you're very good in the software arena. So buy some equipment and start messing with it. In fact, I've got some good FET boards with me. Catch me after I'm done here, and I'll give them to you. You can build your own, and you can start connecting to the chip-on chip. You can wipe its memory out and see that RAM hasn't been erased. You can grab your thermostat, you can rip the keys out of it and start talking to your electric meter. You can even do the voltage glitching attacks if you add another chip to the bottom.
I would say I'm still amazed by the stuff that you've done here.
Thank you.
Really cool. Any questions from the audience? Yes?
Does this just tend to be something that we're seeing as a trend in just about any embedded device out there that's just not paying a lot of attention?
So the question was, is this a trend in embedded systems? And yes, they're not paying attention, but where do they pay attention? If you look across software from multiple vendors and in different areas, no one pays attention until they get a black eye. If you compare the security of OpenOffice and Microsoft Office is actually a lot more secure because they actually take the time to do fuzz testing on their files. They don't catch everything. They don't even catch the majority of things. But comparing that to OpenOffice, where if it works, ship it. And no one is going to sit around and run boring test cases on OpenOffice when they're not getting paid to do it. They'll add the flashy features, but and no company will spend the time making something secure until they see a business return on it. So in the same way that the OpenOffice developers don't need to spend much time in testing, don't need to fuzz test to make sure that all of their file formats are safe, the embedded systems developers don't have to either. And this is an industry that doesn't have the issues of complexity that PC software developers do. So even in writing embedded software, very few embedded developers know about version control. I had a friend who sent a diff file to a microcontroller vendor. saying, hey, we found a bug, we fixed it, here's the patch. And the reply was, what's a patch? So he said, Google for it. They didn't Google for it, they searched their own internal records, and they found this version of patch for 16-bit DOS, which wasn't quite compatible with the GNU implementation. So like they shuffle zip files back and forth, and that's standard. If you need to support two different targets, like right now I'm looking at the reference implementations for JTAG from TI in implementing my own MSP430 debugger, and they just fork it every time they have a new chip come out. So they have 4 different forks of their JTAG client just to program a chip. Yes?
Yeah, my question was actually regarding JTAGs. Normally you use a JTAG interface quite a lot during development phase, but during like production phase, you should only like use it to actually write to RAM and to flash. Couldn't you actually protect against those sort of attacks by disabling the JTAG interface or make it write only?
You can, but there are very good reasons why people don't. If you do this, then it becomes harder to plagiarize the product. It's harder to rip the code out and shove it into another chip. It's harder to do those sorts of things. But what happens if you manufacture 10,000 devices and then you discover that none of them work because of a bug that you need to patch, but you're locked out from the JTAG fuse?
I see, but that was the question. Is it possible to actually disable the JTAG interface, or that's the JTAG fuses that you were talking about?
Yes,
Okay.
so the JTAG fuse is used to disable the access. On different chips, it's implemented in very different ways. In the case of the older MSP430s, once you blow that fuse, you can never repair it as a regular developer. If you go into a chemistry lab and you chip a hole in the glass and squirt a bit of gold in there, then you can repair it. But it's nothing that you can do on an assembly line. So they have the bootloader as a backup method for that. So unlike on many chips where if the JTAG fuse is blown and there's a bug in your chip, you're screwed, on the TI chips you can connect through a serial port and you can program it that way to repair a production line. The problems are that this has its own issues. So now you wind up being vulnerable if either JTAG or the bootloader has a bug in it. And also that programming house will only support JTAG. They won't support reflashing boards by the bootloader, so you'll wind up getting all of the interns at your company to sit and do an assembly line reprogramming to repair a problem. And that's if you can find the problem. Through the bootloader, you're not able to do debugging. You can't watch a register, you can't single step. So figuring out why something doesn't work becomes difficult. And also the security features of the bootloader are to erase all of flash memory, just like the chip-con chip. But part of flash memory contains the values made during manufacturing of the chip that tell you what to set the clock registers to run at a particular frequency. So if you connect with the bootloader, you blow that away, and then you have to patch and hardware your boards by adding a crystal. And all of these headaches buy you nothing as the average developer. Yes, they make you more secure, but they don't make you sell more widgets. And if anyone really wants a copy of your firmware to plagiarize your product, they can do that anyways by other methods. There are labs that you can go to, and you plop down a couple $100 in the low end, a couple $1,000 in the high end, and they come back in a week with a copy of the code. And this wouldn't defend against that. So yes, it can be done, but there's no, or at least there isn't enough economic incentive to do it. Any other questions? Yes?
Yeah, well, thanks for an excellent presentation. You mentioned in one sentence in the first half of your presentation ZigBee and IPv6 and some kind of competition between them. I haven't heard of that before. Could you elaborate?
Yes. So initially there were very many networking protocols for these chips. So the chip itself would be 802.15.4 compliant. All that describes is how to get a 128-byte datagram from one chip to another. It doesn't describe when the radios should be listening. In order for this technology to work, you have to stop listening for most of the time. So one node will tell another to expect the next packet at, say, in 96 seconds. give or take 1 second. And then the receiving chip will turn on only for that window of time, because receiving a packet costs more than transmitting a packet, much more. If you're trying to make these things power efficient, you send a packet at the earliest time that you expect the recipient to get it, and maybe you'll send it twice, because if he spends 4 seconds waiting for your packet to come when it doesn't come, that actually costs more power than you're flooding the network for 4 seconds. And there aren't very good models for how this should work. It's very different from PC networking. TCP rate control and things like that are irrelevant in this arena because of all of the changes that have happened. So there's a point in time when lots of different competing companies decided that they were going to create the networking standard for this. You had 6LoWPAN, which is the IPv6 implementation. There's also Zigbee, which goes as high as the application layers. They even specify how you can turn a thermostat to different settings and things like that. You also had ISA 100 and wireless HART, which are used for industrial control. If you're trying to run a factory, you will use ISA 100 instead of Zigbee because ISA 100 is compatible with all of the SCADA equipment that you're using within that factory, or a water treatment facility, or things like that. So you have drastically different networking standards, all using the same physical layer. That's why there's such a difference, because these things haven't yet settled to a single protocol. Similar to how we were in 1993 to 1995, before TCP/IP went out, when every video game you had with networked play would let you choose between like direct dial-up or IPX/SPX or TCP/IP. These things haven't settled yet. So, yeah, thank you. Are there any other questions, or am I done? Great. Thank you kindly.
Sure. Thank you, Travis.
Excellent presentation.
Thank you kindly.
I was wondering if I could get a copy of the slides to put on the webpage.
Yeah.
Oh, I think we're moving into a coffee break now.
All right.
So we have half an hour of a coffee
Yeah.
break now. All right?
If you want a board, come and see me at the stage. I've got plenty, no charge.
On time. This is amazing.